So hello dear friends, so far we have done the physical aerosols and the physical properties. In this week we will look at chemical processes and some indoor air chemistry, and specifically in this one we will do the basics of chemical reactions. So why do we need to study them? A variety of pollutants are generated indoors or they are transferred from outside. So, in addition to physical processes that we have looked, chemical processes determine the fate of the pollutants, determine also the production of secondary chemicals of importance, which could be, for example, secondary organic aerosols and the oxidative species. So, it is important to understand some formation and pathways for these chemical contaminants. So, why chemical kinetics? Chemical kinetics helps us to understand how the chemical reactions will occur. So, it is important to understand some concepts of chemical kinetics, so that we can go on forward and understand better the indoor air chemistry, or in fact any kind of air chemistry. It is a study of how fast chemical reactions may proceed from the reactants to products, help us to determine the rates of chemical reaction, and also describe conditions using which maybe we can also even alter the rates. So, these kinetic reactions are classified in two broad groups. One can be called homogeneous reactions, which is they occur entirely in a single one phase. They can be gas-gas reactions. So, a gaseous molecule with a gaseous molecule. Whereas the heterogeneous reactions are reactions in which two or more phases are involved. So, such reactions could be, for example, gas and particle, for example, gas molecule on aerosols, gas molecules on surface, gas liquid as well, maybe some reactions in raindrops. So, and solid liquid reactions. In heterogeneous reactions, some of the examples could be, of course, gaseous pollutants with the aerosols, and also of the indoor pollutants at the surfaces of the walls and furnitures, because we have many more surfaces and a much larger surface area available in the indoor environment per unit volume as compared to the outdoor environment. In an outdoor environment, if we look outside, there is air basically, and some aerosols will present, whatever the particles are there, aerosols in the gas in the outdoor air, they will present a surface. Whereas for a given volume, we will have aerosols in the indoor air, as well as we will have the surfaces like chairs, tables, carpets, walls. There are so many more surfaces in the indoor air environment. So, rates of reaction basically are the measure of the change in the concentrations of reactants or a change in the concentrations of the products per unit time. And one can say the speed at which the chemical reactions proceed could be written as, for example, change of concentration in a per unit time. So, for the reaction A plus B gives C, the rate can be expressed in terms of the change in concentration of any of the components. For example, rate could be written as minus delta A by delta T. So, change in A per unit time. For B, or it can also be written as minus delta concentration of B by delta time, or how fast the products will appear. So, delta C by delta T. So, rate can be written in terms of the change of concentration of any of these three. So, rate law basically defines how a rate can be written. So, each reaction has its own equation that expresses its rate as a function of the concentrations of the involved species. For example, reactants, products and catalysts. For example, here the rate is expressed as a reactant, which is A, B is also reactant, C is the product. Here the rate is also a function of the reactant. Here rate is a function of the product. So, each reaction has its own equation that expresses its rate as a function of the concentrations of the involved species. Example, reactants, products and catalysts. In general, rates of reactions will increase because the concentration increases, because we have more molecules of reactants, more molecules of products, and maybe they will collide and make more, there is a higher chance when they collide, that means there is a higher chance of reaction, which means there is a higher chance of product being formed. So, the overall concentration dependence of the reaction rate is basically given in a rate law and rate expression. So, this will be our rate law, and here if the reaction is A plus B gives C, our reaction rate would be K A to power n B to power n, where A and B are the reactant concentrations and M and N are the order of the reactants with respect to specifics. So, how many power M, how many power N, those are the reaction orders. K is a rate constant, and the overall reaction order is the sum of the reactions orders M and N. So, sum of these two. Now, this order of reactions will basically define the power dependence of the rate on the concentration of all the reactants in a chemical reaction in a rate law expression. So, how is the rate dependent on the concentrations of the reactions here? So, we can have we will look at three common types of reaction orders, and we can have n number of orders similarly. So, it is 0 order, first order we will look, and then second order. What does it mean? In a 0 order reaction, the rate is independent of the concentration. So, here for example, we have the concentration, and the concentration is written as molecules per centimeter cube or molecules centimeter to the power minus 3, same. So, here we have reaction where reactant A gives a product P and the order is 0, which means dA by dt is equal to minus K A to the power 0. So, A to the power 0, if we write minus K A to the power 0, this value is 1. So, this value is 0. So, we are left with dA by dt equal to minus K. So, this reaction rate is not dependent on the concentration of A, actually it is a constant rate, and the integrated form of this equation is concentration of A at any time t is equal to concentration of A at time 0 minus K, which is our rate constant, times t. This is quite similar. So, rate constant is basically similar to what we have seen before. So, the take home is in 0 order reaction, the concentration rate of change of concentration, which is the rate of reaction, is independent of the concentration of the reactant itself. It is a constant rate. Then we have the first order reaction. Now, a first order reaction proceeds at a rate that depends linearly on only one reactant concentration. So, even if you have A plus B gives C or whatever, the rate of reaction, which is basically our dA by dt, is proportional to A to the power 1. We see A to the power 1 basically means A. So, dA by dt is equal to minus K times A, where our rate coefficient is 1 by S. So, the solution to this equation, assuming there is no source of A continuously, we have A equal to, which is A, concentration of A at any time t is equal to concentration of A at time 0 multiplied by e to the power minus kt. Some examples of these first order reactions are basically photolysis reaction, where A plus H mu. So, H mu is our photolysis radiation. So, A plus radiation, so photolysis or photoreaction is happening, will give B plus C. These are our products. So, also here we are written rate constant or rate coefficient as K. In photolysis it is often written as J. So, for example, when we are talking about photolysis of A, the rate coefficient will be written as J subscript A. Another example of first order reaction is A plus M, where M is another molecule which is so in excess that its concentration can implicitly be included in the rate constant. For example, the concentration is much higher than the concentration of A, so that the reaction actually only depends on the concentration of A, because M is in abundance. It is so much that there is no need to check, it is always too much. So, how fast the reaction can happen only depends on how much concentration of A we have. So, in this case we have A plus M, and M can be like a regular air molecule, gives B plus C plus M. Then we have now the second order reactions. These are some simplest kind of second order reaction, where the reaction of A with reaction of A gives a product P, and the rate is proportional to the square of the concentration of the reactant. So, in this case the rate is, because we are making we are adding two A's and giving P, we have 1 by 2 dA by dt is equal to minus K A to the power 2, so square of A. In another type of second order reaction, we have A plus B gives C plus D. So, the reaction rate is proportional to concentrations of both the two reactants. So, dA by dt is proportional to A, concentration of A, and concentration of B itself. So, we have dA by dt equal to minus K A, concentration of A, concentration of B. I can even make a bracket here. So, it can be dA by dt. So, this is another way one could have written. So, this is equal to minus K A and B. The way this is a second order reaction is, we have minus K. So, A is to the power 1 and B is also to the power 1. So, 1 plus 1 equals to 2. Also, it is important to note that the unit of K is not just per second, because it is a second order. Unit of K is centimeter cube molecule to the power minus 1 second to the power minus 1. Then I will introduce also the concept of lifetime. because if you remember in the mass balance lecture, we have talked a lot about lifetimes or residence time. So in this reaction, if we have A plus B giving C plus D with a rate coefficient K, the lifetime of A, which is tau A, can be written as 1 by K times the concentration of B. So if we have an example, this we can ignore this. This is, the value is not important right now. If we have NO plus O3 gives NO2 plus O2, tau NO3 can be given as 1 by KO3. So this is the lifetime of NO, and it makes sense because if we increase the ozone concentration, more of NO will be destroyed because this is the reaction. So the more the ozone concentration, the less NO will be living in the atmosphere. It will basically get destroyed faster. Now, to predict and understand these reactions and the magnitude of the reaction rate coefficients and the temperature dependence, we have the first and the most basic theory is the collision theory. Using collision theory, we can understand the magnitude of the reaction rate coefficients and predict them as well. And therefore, we can possibly, once we understand how to predict the rates, we can possibly explain why different reactions can occur at different rates. Now, this theory is based on the collision of hard spheres. It states for a chemical reaction to occur, the reacting particles must collide with one another or the reaction will not happen. So now we will look a bit at the derivation. Excuse me. So in this case, what we have to do is first imagine that the molecules are hard ball. For example, we have a leather cricket ball and we have two molecules, A and B. So now what we will do with this? So I will have, two molecules, one of this color and I should erase this. Let's say a green shape, and we have radius of these molecules. So this is, let's term this RA, and let's term the radius of this as RB. So the assumptions here are as follows. there is no interaction until they come in contact. Okay. But these are also solid spheres, so they cannot come closer than this situation when the distance between their centers is R A plus R B. Basically what it means is, let us assume that these molecules have to collide, but since they are hard balls they cannot squish. But if they are moving and the RB molecules move and it moves like this, it will miss, it will not interact with RA molecule, so there will be no reaction. And if the molecule moves like this, it will collide and there will be a reaction. If the molecule moves in a way that it just touches RA, so in this case excuse me, in this case there will be a reaction. And this is RB. So now we have this collision happening, and this will happen to the extent when the distance between RA, the centers of RA, A and B, so centers of molecule A and molecule B are no further than RA plus RB apart. Okay. Now when molecules react, there will be a rearrangement of sort of the valence electrons. So some energy has to be spent because you are bringing them together and rearranging for this to happen. So they have to cross a energy barrier. Now let us say we have our RA and RB. We have RB and we have okay. Let's say this is RA, a smaller molecule, and this is RB, which is a larger molecule. I will erase this small one. Okay, that's good enough. So I have RB and I have RA. Molecule A and molecule B. Now, if they are moving with velocities VA and VB, let's say they are moving with velocities VA and VB. We will assume that B is stationary for the purpose of derivation. So, relative velocity or the velocity of A relative to B. So, the relative velocity of A is V equal to VA minus VB, because B is stationary, so the relative velocity would be VA minus VB. Now, if A and B approach or A approaches B at a separation less than RA plus RB or less than equal to RA plus RB, a collision will occur. So, now the effective cross section area available for A to collide with B is how much? This is the total zone which is available. I will mark it in red color. This is the total zone which is available. So, the cross sectional area is this one, and the radius of this sort of sphere is R equal to R A plus R B. So, the effective cross sectional area for A to collide with B is pi R square. So, now if we have one A molecule, I will just type it in text. If we have one A molecule colliding with NB, stationary molecules. Stationary molecules in this sort of region, then A will sweep an area of how much? Pi R square multiplied by the A will sweep out a collision volume of pi R square multiplied by V. So, I will write of pi R square V and collide with I will just write here, and collide with how many molecules? Pi r square V N B molecules. Okay. Now if we have Na molecules, so Na I will write, okay, N A molecules of A. Na molecules of A, then total number of collisions per unit volume per unit time is given as Z equals to Na Nb pi d square V, and the unit would be centimeter minus 3 second minus 1. Okay. The mean speed of molecule, mean speed for relative velocity of A is given as, with B basically is given as 8 kb t mu pi to the power 1 by 2, and kb is Boltzmann constant. So that's our relative velocity, and mu is given as MA MB divided by MA plus MB, where M are the masses of A and B. So now we will have the overall reaction or number of collisions of between the number of collisions between A and B as Na and B pi d square and then V bar. So 8 K P T, T is the temperature, pi mu to the power 1 by 2. So for now, if we have this reaction A plus B giving some product, not all the reactions will lead to product, because not all reactions will have the enough kinetic energy. Not all collisions, not collisions will have sufficient kinetic energy to sort of cross. For example, to cross the energy barrier related to rearrangement of the valence electrons. So the fraction of collisions which have energy greater than, so fraction of collisions with energy greater than an energy barrier E is E exponent of minus E by R T, where R is the ideal gas constant and R is the gas constant and E is the energy barrier. So now our rate of reaction, and E would be in units, for example, kilojoule per mole. Okay. So now the rate of reaction between A and B can be written as pi d square square root of 8 K B T by pi mu then exponent minus E by R T multiplied by NA and NB. Now these are our concentrations. So basically R is proportional to, this is similar as R being proportional to NA times NB, right? Concentration of A and concentration of B. So the rate coefficient becomes and so pi d square eight K P T by pi mu 1 by 2 multiplied by exponent minus E by R T. This is often written as a parameter A. So then RA becomes RAB becomes A exponent minus E by R T. So A is the collision frequency factor. So A is basically the frequency of reaction. So A denotes the frequency with which reactants collide, and remaining, which is E by RT, is the fraction of collisions with sufficient energy to overcome the energy barrier. So A excuse me. So A energy, I'll just write barrier here. So A, the order of magnitude of A is 1.5 into 10 to the power minus 10 centimeter cube molecule minus 1 second to the power minus 1. This is our typical value of A. So now we are ready to go to the next slide. So actual A factors. So here we had the theoretical order of magnitude of A, which is theoretical. So this I will say or we will leave it at that first. So this is our theoretical, but the actual A values are substantially smaller than those based on the collision theory, which we just highlighted earlier. This is because of several reasons. One is that molecules are assumed to be hard spheres, and the molecule structures are not considered to be important. But in reality, molecules can be more reactive or they can be less reactive. So some collisions will be less effective if the reactive ends of two reactant molecules are not pointing at each other. Basically, here what it means is we have A for OH plus CH3Br giving water and CBr3 is 1.8 10 to the power minus 13, which is much lower than 1.5 10 to the power minus 10, almost 1000 times lower. Now why? Because CH3Br has a it is one this is CHBr3, excuse me. This is CH3Br. So we have OH plus CHBr3, again the same mistake I am doing. This is CHBr3. So this is a good example. OH plus CHBr3. So we have one hydrogen which is shielded by 3 bulky bromine atoms, and our reaction is OH giving H2O. So this OH must approach and collide with the H part. If it collides with any other part, Br or anything else, there is nothing going to happen. The OH must approach the H part of CHBr3, and this H part is shielded by 3 bulky bromine atoms. So OH should be precisely be directed towards the shielded H for reaction to occur, and it is we can see easily that the reaction rate constant is 1000 times smaller than what it was possible, because we have much lower possibility of the reaction being happening. So in summary, basically, in collision theory of reactivity, reactions will occur when the reactant molecules will effectively collide, not just collide, but effectively collide. And also, for an effective collision to occur, the reactant molecules must be oriented in space correctly. For example, in general terms, if A plus Bx gives V plus Ax, A has to collide with X. Here, A is colliding with B, like our OH was colliding with bromine, so it's no use. A must collide with X to cause production of AX. So for effective collision to occur, the reactant molecules must be oriented in space correctly to facilitate breaking and forming of bonds and the rearrangement of atoms and form products. The next is we have to look at activation energy. So we will just look very briefly on the potential energy surface for a bimolecular reaction and the activation energy associated with it. So we are going to see, consider the potential energy for a bimolecular reaction, and this is our bimolecular reaction. A plus BC gives BC, and it's a reversible reaction. So we have A plus BC can give A B plus C. Now A plus BC has to give BC plus C. So let us look at in this slide how. Now we have, let's say, distance. So we will just say this is my or maybe I'll just better on the whiteboard. So we have here we have potential energy. And here we have, let's say, distance along reaction coordinate. So we start with the reactants A plus BC. Now the energy of the reaction system is going to increase as they approach each other, and as they form like a situation which is A, B, C, and this is symbol is for like an excited species. So the overall energy has increased, and this increase is, let's say, let's say this is EF. This energy is EF. Now after this the energy will start to decrease again, and this activated complex is short lived. So this short lived complex will break down and reach to some another point, which is the product. So let's say we have reached now the product AB plus C, and we have come down. The potential energy decrease is this much now. Let's term this ER. So now we have reached for some product now. So this energy is basically our initial energy that has to be provided. So activation energy for the EF, which is the forward reaction, is EF. To make the reaction from A plus B to B plus C, I must provide an activation energy of EF to form this transient excited state. If I was to go for the reverse reaction, A plus B giving A plus BC, we must again reach A, B, C state, which means I need to provide an activation energy of ER, which is much higher than EF actually. So this is the energy of activations from either the forward reaction or the backward reaction, and the enthalpy of the forward reaction is basically delta H, and I will term this as HF, which is equal to EF minus E, and we can see this is I'll just make a smaller minus sign, EF minus ER, and here we see delta H is negative, which means the reaction is spontaneous. If we were to go from A B plus C to A plus BC, we need a higher activation energy, and also our delta H would be positive, which means we have to, it's an endothermic reaction, we have to basically provide energy or provide more energy. So this gives us an understanding of the potential energy barriers to different reactions. So basically the height of energy barrier depends on the amount of electronic rearrangement that is needed. So from reactants to our higher transient state. In general, molecule-molecule reactions require a high degree of electronic rearrangement and have a large activation energy barriers, because molecule are colliding, so they must have more rearrangement is required, so you need more energy to make all these rearrangements. In radicals, which has a free free dot, the radical molecule reactions require much smaller rearrangements, and the activation energy barriers are quite small. They may often just require transfer of one atom. So these are quite small energy barriers, and the reactions can happen also quite readily. So in summary, we can have a situation where molecules must provide, or molecules must have a minimum amount of kinetic energy for an effective collision to occur. So, we will have this energy of activation that is needed for the reactants to lead on to the products. Okay, there's some. And a higher activation energy generally means that fewer molecules will have sufficient energy for the collision. So, now we had looked at the basics of what is required for the chemical reaction to occur. We will touch upon the gas surface reactions because these are also important for our indoor surfaces. So, many reactions will involve gas molecule striking a surface. For example, if it is air, the gas molecule is striking an airborne particle, an airborne aerosol. So, the number of molecules of gas A striking a unit area per unit time would be 1 by 4 number of molecules multiplied by VA, which is the VA is the mean speed of our gas molecules. And if these gas molecules are colliding with particles of total surface area per meter cube of air as AP, which is so per meter cube of air how much particle surface is provided by the aerosols. So, there will be number of collisions per second with particles of total surface area AP centimeter square per centimeter cube. So, the total number of collisions of A molecules will be 1 by 4 Na V mean velocity of A multiplied by AP. Now, this is the number of collisions, but we also know that the reactions are not 100% efficient. So, if we have gamma as the reaction efficiency, which is generally determined experimentally, the rate of reaction R will be 1 by 4 gamma NaVA multiplied by AP, and the rate constant for reaction would be not this, it will be 1 by 4 basically, and this is we have to rewrite as 1 by 4 gamma VA AP multiplied by Na. So, Na is our number of molecules. So, this is sort of our concentration, and this all will become K. So, K would be our rate of reaction, rate constant for reaction 1 by 4 gamma VA bar multiplied by AP. So, this will be our rate constant for the reaction. So, we have seen basically about the collision theory of reactions, what is needed for reactions to occur, what could be the theoretical collision frequency versus the actual collision frequency, and also a bit on the surface gas reactions and how the rates are similarly derived. Now, generally the rate of reaction is dependent on the reactant concentration, because the more the number of molecules of A, let's say A and B molecules, if there are more the number of these molecules, the more there is chance of collision. The more there is chance of collision, the more there will be a possibility of the product coming out. Then the physical state of reactants and the surface area available for the physical state of sort of the particles, for example, is also important, because the more the surface area available for example gas surface reactions, the more the reaction rate will go forward. Then we have the effect of temperature. We saw that the sort of the efficiency of the collision also depends on temperature. Sometimes presence of catalyst will help, and also radiation depending on the reaction in question. For example, in reactant concentration at a fixed temperature in absence of catalyst, let us see this rate, basically rate of reaction. So, increasing the reactant concentration will of course increase the rate. This is because the number of molecules per unit volume has increased and thus the collision frequency has increased, which ultimately causes an increase in reaction rate. If the reactant molecules will exist in different phases as in a heterogeneous mixture, the rate of reaction will be limited by the surface area of the phase that is available for the contact. For example, if a solid metal reactant and a gas reactant are mixed, only the molecules present on the surface of the metal are able to collide with the gas molecules, because the inside part molecules are not accessible to the gas. Therefore, increasing the surface area of metal by pounding it flat or cutting into many pieces will increase the reaction rate, because now we have more surface area available for the reactions to take place. Increase in temperature generally increases the reaction because it raises the average kinetic energy of the molecules, and therefore, there is chance that more proportion of molecules will have enough energy to cross the energy barrier. So, more molecules will have minimum energy required for a effective collision. This is, for example, we have a curve, kinetic energy on the x axis and fraction of molecules on y axis, and we have basically the more molecules crossing the energy of activation, more fraction at higher temperature. Catalysts generally are accelerating reactions without necessarily being consumed, and they will provide an alternative reaction pathway to the obtaining of products. Finally, we have the photochemical reactions, which are the radiations, which basically means that molecule or molecules at ground state will absorb some sort of energy, photolytic energy, and the molecules will reach now an excited state, and once that excited range state is reached, some molecules will return to the ground state, but for some molecules the excitation will lead to a formation of new molecule, which would be the product. So, photochemical reactions would be essentially processes caused by the absorption of light energy, in which the physical and chemical properties of molecules will become different from the original ground state, and molecules can then form new structures. The efficiency of such a reaction is written as quantum yield, which is basically number of moles of reactants consumed or products produced per mole of a photon of monochromatic light absorbed. Of course, because efficiency is there, because some reactants will go back to the original state. There are several kinds of photochemical reactions. Photodissociation, where we have AB, which is dissociated by light energy. Then photo-induced rearrangement, for example, isomerization, A rearranges to B. Photoaddition, in which A plus B gives AB. We have substitution, A plus B gives AB plus C. So, here C is substituted by A. And then photoredox, where we have A plus B and light energy is basically leading to addition or removal of electrons. These are just some examples what can happen. For example, nitrogen dioxide can break down to oxygen atom and nitric oxide NO. Also, ozone photochemical reactions are highly driven by photochemistry. So, we have the oxygen molecule O2, which is when ultraviolet rays are incident on oxygen molecule, we have two oxygen atoms being produced, and then this oxygen atom being produced reacts with the O2 molecule to give our ozone O3 molecule. So, solar radiations are absorbed by molecules, then collision may occur or rearrangement occur, and may lead to formation of products. Example is photochemical smog, where NOx and VOC react to form our brown haze, and in outdoors NOx, VOC, O3 aldehyde, PN are the primary and the secondary pollutants that are somehow influenced by the solar radiation. Here we have basically one case where NO2 leads to NO plus O. This O reacts with so this O reacts with O2 to give O3. Now ozone can react with NO and form NO2 again and give oxygen, and this can keep on happening. NO2, which is nitrogen dioxide, can react with some hydrocarbons here represented as RH, which may for example be produced from VOCs, and form peroxyacetyl nitrate, which is PAN, or NO can react with oxygenated organic and inorganic compounds. For example, here we have written ROX to form NO2 nitrogen dioxide. I will write it here to make consistent. To use consistent terms, nitrogen dioxide. Oh, sorry, this was correct actually. It reacts with, this is okay. Oxygenate organic and inorganic compounds ROX react with our nitric oxide and produce more nitrogen oxides, in this case being NO2, and then again NO2 goes back to here and starts this reaction again, and NO is here. So there are a lot of reactions that are possible with NO2 and NO driven and ozone, which lead to formation of PAN or NO2 itself. So this is the way photochemistry could work. So in this lecture, in summary, we have covered basics of chemical reactions and looked at reaction rates using collision theory. We have looked at the concept of activation energy, potential energy barriers, gas surface reactions, and photochemical reactions. So now we have very much sufficient background to move forward and go towards indoor air chemistry.